Welcome to the Greek Ship Corrosion channel. My name is Maryam Ehteshamzadeh. I'm a researcher in the field of corrosion and protection of materials. Chapter 5, Section 1. Corrosion of active passive type metals and alloys. 1. Passive layers. 2. Stainless steels. 3. Polarization behavior of active passive metals and alloys. The references are shown here. History of passivation process. In the mid-1800s, chemist Christian Friedrich Schonben discovered the effect of passivation. After dipping iron in concentrated nitric acid, he found that the iron had little or no chemical reactivity compared to iron that did not receive the concentrated nitric acid treatment. His name for that lack of chemical reactivity was the passive condition. In 1913, Harry Brearley of Sheffield, UK discovered rustless steel. Although there had been many prior attempts, Brearley has been credited with inventing the first true stainless steel, which had a 12.8% chromium content. He had added chromium to molten iron to produce a metal that need not rust. Chromium, when exposed to oxygen, air, forms a thin film of chromium oxide that covers the stainless steel surface and protects the underlying iron from rusting. Stainless steels are corrosion resistant, but they are not completely impervious to rusting. One common mode of corrosion in corrosion resistant steels is when small spots on the surface begin to rust because grain boundaries or embedded bits of foreign matter such as grinding swarf allow water molecules to oxidize some of the iron in those spots despite the alloying chromium. This is called rouging. Water and temperature cause rouging of stainless steel. Rouging will be introduced by the end of this video. Which metals show active-passive behavior? An active-passive metal has a transition where it changes from active to passive behavior. Aluminum, titanium, zinc, chromium, iron, cobalt, nickel. Standard potentials are shown here. Aluminum negative 1662 millivolts versus SHE. Titanium negative 1630. Zinc negative 762. Chromium negative 744. Iron negative 440. Cobalt negative 277, nickel negative 275. Stainless steel as invincible as Achilles. Stainless steel has revolutionized the modern world and has found applications in almost every manufacturing sector, from healthcare and catering equipment to the automotive and construction industries. Stainless steel is a core and integral part of industries. It enables creativity in applied form and practices scope in important engineering services. Endless sectors are served with their versatility. The stainless steel industry is the most dynamic and largest industry associated with the oil and gas industries worldwide. Stainless steel is a convenient and cost-effective ideal choice for the oil and gas industry. Stainless steel are iron-chromium alloys. Furthermore, it has outperformed more traditional competing materials such as copper, aluminum, and carbon steel. The oil and gas industry is vital to the global economy, influencing transportation, electricity, and manufacturing. It comprises three main segments. Upstream. This process involves the exploration of underground natural gas and crude oil wells and drilling. Midstream. In this process, crude oil is transported, stored, and processed in the refinery. Pipelines and oil tankers can be used in transportation. Downstream. This process includes refining, crude oil filters, and purification of natural gas takes place. Stainless steel, also known as Inox. Stainless steel, also known as Inox or corrosion-resistant steel, is an alloy of iron that is resistant to rusting and corrosion. The term inox is a collective colloquial term for a steel-based material developed over 10 years ago, which has high resistance values against corrosion and acids, and it represents a number of chrome-nickel steels, stainless steel, to which other elements are also added. Stainless steel's resistance to corrosion results from the 10.5% or more chromium content, which forms a passive film that can protect the material and self-heal in the presence of oxygen. Self-healing materials refer to substances that have the built-in ability to automatically repair damages to themselves without any external diagnosis of the problem or human intervention. Oxygen is essential for the forming of a passive layer on stainless steels. Passivation can be represented by a schematic plot of corrosion rate as a function of oxidizing power of the environment, as shown in this graph. Schematic representation of the effect of increasing oxidizing power of the environment on the corrosion of an active passive type alloy such as stainless steel. Consideration also should be given to adjustments in the environmental conditions to provide oxidizing conditions that will form the passive film on the metal surface. An arbitrary scale is used to show the oxidizing power of cathodic reactant or potential of metal relative to solution. This is for the horizontal axis. A logarithmic scale is used to show the corrosion rate or corrosion current density. This is for the vertical axis. No passive film formation, passive film formation, passive film protection, transpassive or passive film destroyed, displaced curve due to anions such as chlorides are shown here. Representative anodic polarization curve for iron in a buffer solution. The passive behavior is characterized by three parameters. 1. The critical current density, icrit, that must be exceeded on an upscan of potential to initiate formation of the passive film. 2. The passivating potential, EPP, at which the current density begins to decrease. 3. The magnitude of the current density in the passive condition, IP, critical current density, passivating potential, current density in the passive condition. The magnitude of the change in current density between I critical, icrit, and IP is of major significance, since this change indicates the effectiveness of the passive film in reducing the dissolution or corrosion rate at the anode surface. To be of practical significance, the ratio IP over icrit should be 10 to the negative power of 2 and preferably smaller. Ratios as low as 10 to the negative power of 6 are observed. Values of IP are frequently of the order of 10 to the negative power of 6 milliamperes per square meter, corresponding to corrosion rates of about 25 micrometers per year, 1 mpy or Ms penetration per year. More about rouging. What happens when rouging occurs on stainless steel? Rouging is a form of corrosion that happens to stainless steel and needs to be removed to avoid further damage or contamination of the production. The most common type of rouging is a layer of red-brown coating covering the stainless steel surface, as you can see in the picture. More pictures of rouging are included here. Why does rouging occur? It is caused by various factors, including low percentage of oxygen combined with high temperatures. In systems with high temperatures, the risk of rouging is higher due to the iron oxides multiplying. The risk of rouging also increases when there has been inadequate passivation, poor welding, oxides being present, or other inadequate surface treatments. How to deal with rouge? There are various ways in which rouging can be removed from an affected system. 1. Conventional pickling. 2. Electrochemical weld cleaning. Conventional pickling will dissolve the passive layer and strip back the rouge, leaving a clean surface. The negative side is that this process will etch the surface of the steel, roughening and dulling the finish. Electrochemical weld cleaning is a much quicker process due to the rouge being very easy to remove with this method. Passivation is required after derouging. Thank you for your time. Challenge number 10. If you like to challenge yourself, please answer this question in the comments below. How to passivate an industrial equipment after derouging?